Alright, let's start off with a little review of what we did in the last video. So it was basically just definitions and some quick examples, and so let's quickly outline them here. Okay, so we started with distance. Okay, remember, distance was just a measurement of how far an object has traveled. Okay, remember, this is a scalar number, so there is no directional component to this. So if you have a measurement that you've measured on the ground, doesn't matter which direction you're going to. If I went 10 meters north and then 10 meters south, I don't care about the direction. It was just 10 meters, a total of 20 meters. Displacement, on the other hand, does care about the direction. So we can define it in a way that says it's how far an object travels from its starting point directly to its endpoint. Okay, so we already defined it mathematically as final position minus the initial position, and that's what we're saying here. All we care about is how far away am I from where I started to where I ended. I don't care, anything in between, I don't count. I draw a line from where I started to where I ended. That is my displacement. Okay, one way to think about it is imagine like walking around in a city. I could walk around blocks and walk off path and everything else, but when I look at the map of where I started, where I ended, I draw a straight line to those points. There's my displacement. Okay, and in the other example I gave for distance, if I do 20 or 10 meters north and 10 meters south, well, if I add those with their directions, my displacement's 0. So remember, direction matters for displacement. It does not matter for distance. Then we also defined two other things. One was average speed. Remember, average speed was the rate of change of your distance traveled. So mathematically, we would say average speed is equal to the distance divided by the time. And since distance was a scalar quantity, so too is the average speed. The other quantity was average velocity. Remember, average velocity was the rate of change of an object's position. Okay. Now, by definition, the change in an object's position is called displacement. So that means your average velocity as an equation would be written out as displacement divided by time. And because displacement's a vector, average velocity must also be a vector. Now, before we go any further, let's take a quick note on mathematical symbols that we will use to talk about these physical quantities. Okay, it shouldn't, I just want to say it quickly. Most of it's self-explanatory, but we're going to go through this anyways. So the first is when we talk about position, you'll usually see that written out as either an x or y variable, because position is either measured on a horizontal number line or a vertical number line. You've seen that in your math class. That's why we use it. Now, at the same time, in this class, in AP Physics, one of the things we might end up using is other letters to represent distances or positions. By that point, you should be so comfortable that we can call it whatever we want and you'll be okay. For right now, x and y is good enough for us to tell positions, which means our displacement would then be written as either a change in x or a change in y. Okay, average velocity, you'll see it written as a v for velocity, and if any of you have taken a statistics class before or have seen it in your math class, average is usually denoted with a bar over the variable, and we're going to do the same here. So when you see that bar written over the variable, we're talking an average velocity. And then average speed, well, since for the most part average speed is simply the scalar version of average velocity, you'll see it written as simply the average velocity with an absolute value symbol, implying that we're removing the direction from the number. Okay, so those are the basic symbols we're going to use to talk about these first ideas in physics. So let's start with the first one, which is uniform motion. Okay, when we say the term uniform, we're referring to an object, okay, that moves with constant velocity. Okay, nothing too complicated about that. Uniform motion means a constant velocity. All right, so if we're looking at, say, an object, we're watching a car drive down the road or watching somebody run track, for example, and we want to graph that motion. Okay, let's take a second and talk about what should a position time graph look like for an object in uniform motion. So since it's a constant velocity, that means that your position is changing at a constant rate each second. Okay, if I'm going at a constant velocity, say of 2 meters per second, that means every second I have changed my position by 2 meters. Okay, so on this graph, on this position time graph, position on the y-axis, time on the x-axis, a uniform motion or an object in uniform motion, their data would graph such that we get a fairly straight line. So the data points represent measured data, and then we use a line to best fit that data, and it should be relatively straight. And if we were to look at the change from data point to data point, we should see that the change is always the same. Okay, now on the graph, what do you see me doing by these dashed lines? If I'm looking from one point to the next, what I'm really looking at is the slope. Okay, now how do we calculate slope? You'll remember from your math class, it's simply rise over run. Okay, but our variables on the axes have changed. For example, on the y-axis, we're now graphing position. So the rise would simply be a change in position. And on the x-axis, which is now time, the run would be a change in time. Well, by definition, this is displacement divided by time, which is our average velocity. So we see that on a position time graph, the slope tells us the average velocity of an object. Now we've already done some in-class practice on this, so this shouldn't be a new idea. But here we're trying to formalize that. The slope on a position time graph is your average velocity. Okay, but now what if an object's not in uniform motion? Okay, if uniform motion means moving at constant velocity, then what about the more realistic world where objects don't move at constant velocities? So the simplest form of that would be we have a position time graph. So position on the y-axis, time on the x-axis. Now this would produce, for non-uniform motion, a curve. Because each second, because our velocity is changing, we will change our position by a different rate each time. Okay, so if I were to graph this and get a nice little curve, you'll notice that the positions over later and later times are increasing at greater and greater rates. So this implies that my speed must be increasing each second. Now, if we did what we did in the last graph, right, I picked 2 points on this curve and I connect them with a secant line, I could find the slope of that line and I would get an average velocity over that time interval. But you'll notice that that curve, what I've skipped over, implies that there's a lot more going on with the object. At earlier times I wasn't going very fast, and at later times I was going really fast. Well, in this class we want to know how to analyze all those individual velocities. Okay, so again, you'll notice at the bottom point there's like a tangent line here where there's a little bit of a straight line that has some slope to it, but each point, that straight line increases in slope. That must mean the speed is increasing. Again, slope on this graph means average velocity, and each slope is getting greater. So my average velocity over each small time interval is increasing. So each of these lines represents an average velocity But this average velocity is over a very small time interval. Okay, so we can't keep using two average velocities and have them mean different things. So we're going to redefine this one that I wrote in blue. Okay, we're going to say if the time interval is infinitely small, which is the goal of this graph, mathematically we're talking about a limit as our time, change in time, approaches zero. Okay, then we say that the average velocity over this tiny time interval is called the instantaneous velocity. Okay, and as a symbol, we would just use the letter V. Now, the reason why it's still an average is mathematically, we talked about this before with our calculus lessons. I can't divide by zero. So if I'm talking an instant, there still has to be a tiny change in time. It still has to be a delta t in the denominator. And so over a delta t, we're still talking average. But if I make that delta t really tiny, then that average is practically instantaneous. So we'll call it instantaneous velocity. So mathematically what we're talking about is instantaneous velocity is the limit as t goes to zero of your average velocity. The average velocity, of course, is your displacement over time. And we learned from our little calculus lesson that from this equation, this is the definition of a derivative. So it turns out that our instantaneous velocity is just the time derivative of position. So let's map out the process here. So let's start with position. And from position, we can go to velocity. Now we've already discussed ways that we can do this. Okay, the first way to go from position to velocity is it's a rate of change. Okay, that's what it means, right? And one of the ways we could find that was simply looking at the slope of a position time graph. Now, that each of those is the definition of a derivative. Rate of change is a derivative. The slope on a position time graph, that would mean the derivative at a given point on a position time graph. So that's how we get from position to velocity. Now, what if we want to go backwards? Okay, well, one way to think about it is if velocity is the rate of change of position, then position must be the vector sum of all position changes. Okay, so what does that mean? The vector sum of all position changes. Vector sum means we care about the direction when we combine the numbers, and we're looking at how the position is changing over some time interval. Well, that is referred to as the total displacement. Okay? Now, what about the other way? For a graph, if velocity is the slope of a position time graph, what we find is that position, rather the change in position, the total displacement covered, would actually be the area that's under a velocity time graph. So notice it's a different type of graph. Velocity is the slope of position time, but position, or rather the total change in position, would be the area under a velocity time graph. So if we looked at a velocity time graph, so here's a generic curve, the question would be how much distance, or rather how much displacement is covered in a certain time. Well, let me show you how this mathematically ends up working that way. So let's pick two arbitrary times, say t1 and t2, and I want to find the area under the curve between that interval. During our calculus unit, we already learned that area, mathematically, is an integral. of our function over that dependent variable. In this case, our function would be velocity, and it's over a time interval, so velocity dt. And we're doing the sum, so integral, of all the little areas, the little rectangles under there. That's where the vt comes from. Now, we already know that velocity is a derivative of position, so let me write that in here. So I just substituted the derivative of position with time for v, and notice the dt's cancel out. So now what I have is an integral of just simply dx. Now what do I put for the limits? Well, the limit should have been t1 to t2, but now that t's been canceled away, what I want to look at then is how does the x change? Notice, now it's the integral of dx. So what are the x limits that match up to those t limits? Well, if the limits were going to be t1 to t2, we can just say the position at t1 and the position at t2. So x1 to x2. Now, you know the process of this. This is an antiderivative. And the antiderivative of dx would just be x. Then you do upper limit minus lower limit. So what you're really doing is x2 minus x1. But that is just the change in x, which we called our displacement. So as you can see, it's true. The area under the graph gives us the total displacement. And that's a way we can get from velocity back to position, is this idea of antiderivatives in area. Now, keep in mind this is only talking about displacement. If I wanted to find the position, so say some final x position, I would need to know what position did I start with plus the displacement that occurred. And so if I'm looking at a graph or I'm given an equation for velocity, how do I find the displacement? Well, I simply do an antiderivative. So if I know where I started, then I do an antiderivative, I can figure out the exact position where I end.